everyone for coming this morning to another finite element seminar at Livermore. It's my great pleasure today to introduce Professor Jed Brown. He's from CU Boulder. I think you've been there for more than a decade at this point. Known Jed for a long time, worked together under the ACP in the CEED Co-Design Center, and actually today he's going to talk about libCEED, which came out of that work. If you haven't read Jed's bio on his website, you should go and do that. I'm not going to spoil it, but it's kind of legendary. He's a really great guy, and I'm looking forward to his talk about libCEED and its recent developments. Jed, thanks for coming. The floor is yours.
Wonderful, thanks. Yeah, so I'm going to give you a tour of some of the recent applications that we've been working in with libCEED. I'll give you a little bit of our philosophy, and hopefully, if you know about libCEED, there will be some interesting nuggets in here. And if you're not familiar with libCEED or this approach, it'll also be accessible and give you some ideas. So if we go back almost 20 years, David Keyes was giving talks, and one of the things he was observing is the cost of computing was going down rapidly. And this, he was predicting leads to using computing, modeling, and simulation-based methods for many more things. I think there was a nugget of truth in that. I think maybe we kind of underestimated how much people were actually the bottleneck, more than just the cost of computing. But what I want to focus on is how we use computing differently and should embrace that difference, because it's not that everything got cheaper, but the relative costs changed. And I think that has influenced behavior more than the absolute cost. So if we look at the setting of nonlinear solid mechanics, we have in kind of standard industrial state of practice, which are largely low order methods. When using tetrahedra, that's going to be quadratic because the locking problems with linear tetrahedra are too bad. But it's mostly low order assembled matrices, lots of like algebraic multigrid, sparse direct solvers, not a lot of matrix free. And I think there were two myths that have been accepted. And myths aren't any good if they don't have a nugget of truth to them. So I want to explore these kind of briefly. The first is that high order doesn't help because real problems have singularities. This is true, real problems have singularities. You will not realize high order on an industrial problem, but that doesn't tell the whole story. And the other is an assumption that matrix-free methods are meant for very high order methods, like you would get with spectral elements, and are not appropriate if you don't actually use those. So let's explore the first part. Yes, it's true. Industrial models are just riddled with singularities all over the place. There are reentrant corners, there are jumps in coefficients. We cannot actually observe high order accuracy on almost any industrial problem. There are too many singularities. And so there is a mathematician's approach to this problem, which is to use HP adaptive finite elements. And that allows you, say in this diagram, we are on a log error versus linear axis here. And you can get a kind of straight line instead of something that curves outward on that error plot. Those HP adaptive methods lead you to elements where the darker red here represents a higher order element. And so you have really interesting refinement patterns around the corners. Say if we were to look up here, you have this kind of interesting refinement pattern. The thing is, nobody really uses meshes like that. When doing analysis, you get meshes that are relatively coarse. There just isn't room for this kind of adaptivity because you can get to sufficient accuracy on relatively coarse meshes. And so I think we should calibrate our understanding to what are efficient methods on coarse meshes, often like the coarsest mesh that adequately resolves the geometry. So we're going to take a test problem over here on the right, just take a peek at what that looks like. So I'm going to plot here relative error versus number of degrees of freedom, and this on a log-log plot. And one thing we can see here is, say, your very standard method, say with linear elements, delivers this line. This line has the same slope as higher order. So the x's here are quadratic element order, whereas the circles are linear. And those have the same slope, but they don't have the same constants. Now, if you were to go p-refine and not enrich the geometry, then you get this hideous anti-convergence here. Now, the reason for that anti-convergence is because if you're stuck with linear geometry, and if I were to look back at this problem, you can see there are like very weakly reentrant corners around as you go from element to element. This is meant to be a circular hole, but it's only resolved on a linear mesh. And if you do that, then you better resolve those geometric artifacts of the mesh processing. But if you can enrich the geometry so that you follow, you get this curve down here on the bottom, which is by far Pareto optimal among the points that are out here. So even if you need relatively coarse tolerances, if you're on very coarse meshes that barely resolve the geometry, still turning to higher order methods, be it quadratic or cubic, tend to be very practical. That is actually the best way to deliver accuracy. It's much better than just straight H refinement. So if we have assumed that we're using assembled matrices, then you're going to say those higher order methods cost more per degree of freedom than the low order method. And so this x-axis is being overly generous to the high order methods. And maybe when we correct that, you don't actually see this order of magnitude difference, say here between the points on the left and, say the round gold circles that I had highlighted earlier. Maybe the higher order effectively has a higher cost, and so maybe there's pretty marginal gains there. The issue is we compute on modern hardware, and modern hardware has delivered us flops much more than it has delivered us bandwidth. And so when you look at the relative cost of flops and bandwidth, flops are now very cheap. Bandwidth is the expensive thing. And so that actually changes our assumptions about what data structures would be appropriate and the relative cost of these methods. So on the left here, I have bytes per degree of freedom. And we see that even for linear elements when solving vector problems, that there is an advantage to matrix-free representations. And as you go to higher order, even quadratic and cubic already reveal quite huge benefits to using matrix-free representations. That crossover point in the right plot is pushed off, and so maybe quadratic and cubic are kind of middling benefits, and when you get beyond cubic, then you start seeing this clear benefit. But that is a very dated performance model. It really hasn't been true since like the 90s at best. This is also a result of just fundamental physics in how much energy it takes to move bits around or to compute flops. So you see here, through all the levels of the memory hierarchy that is in the middle, there has been essentially no progress from 2008 to 2018 and continues to be essentially no progress through to today. On the far left side, we see the cost of flops are dropping drastically. And that has continued since 2018, though in the past few years, a lot of attention has gone towards reduced precision rather than improving double precision. But regardless, that cost to do the flops is where advances in manufacturing and design of chips has really seen an improvement. We're not getting it in the cost of moving through the memory hierarchy. And so the result is that matrix-free methods are already faster than assembled linear methods, like Q1 elements, linear elements. So if someone were to deposit into device memory at zero cost an entire assembled matrix, your fastest solver is to not use it. Now, that has interesting knock-on effects. So, for example, this plot over on the left is in a compressible turbulence simulation using a package called Honey. And here we see that the cubic elements are by far the fastest. They also don't have to build a matrix. And so we don't see this big red cost related to building a matrix that you see over on the bars here for sparse representation. Instead, with the matrix-free representation, we don't have to do that. There's a little bit of setup in computing, say, point block diagonals for preconditioning, but we don't need to actually assemble these data structures, and therefore a lot of costs just go away. That said, even the matrix vector product is much faster in matrix-free representation. So that's the purple bar. It is faster for all orders of discretization, especially, say, quadratic and cubic. So what we've seen from the performance model and the simulation in isolation also applies to production simulations. That's a pretty cool result. Over on the right in that figure, this is for a structural mechanics problem. And we observe essentially the same thing, that when assembling using sparse matrices, and this is like time to actually solve a complete nonlinear problem, using the sparse matrices is very inefficient relative to using the unassembled representation and the matrix-free preconditioning that we'll get into. So we do need effective preconditioning. The approach that we advocate and have implemented throughout Radel is to be matrix-free on the fine levels, where you may have high-order elements. And high order can mean just quadratic. Like if you mesh your geometry and the coarsest mesh you can have delivers engineering accuracy with quadratic elements, then absolutely use quadratic elements. That's totally fine. But it could be cubic or higher order than that. So we are matrix free on the fine levels, and then we do turn to assembly, but those are for once we have coarsened using P multigrid to linear elements. For algebraic multigrid, depending on the problem, we're using smooth aggregation, primarily through PETSI, or we're using hyper, also accessed through PETSI. So that depends on the nature of the problem. In general, the pattern here is while we compute the residual, there will be some intermediate data that we store at quadrature points. If you had to compute lots of residuals, you could save a little bit of bandwidth. You don't really save floating point operations, but you could save a little bit of bandwidth in evaluation of the residual if you, had a way to not write out that intermediate data. But when using Newton type methods, just speculatively computing or storing what you would need at quadrature points tends to be a good trade-off. And then when applying the Jacobian, we use that stored representation at quadrature points. And you can be really creative about what exactly should be stored at those quadrature points. So if you look at nonlinear solve efficiency, I'm going to look at quadratic and cubic elements here. You can see A100 based machines and MI250X machines are delivering very similar performance for quadratic elements, and the NVIDIA devices are a bit better. This is normalizing per GPU, like per logical GPU. So you can debate whether that's the right thing to normalize with respect to. I think it is interesting that operator application in our experience has consistently been faster on the NVIDIA devices, as long as you're normalizing in that way. However, assembly of preconditioners, so this is like the setup for the algebraic multigrid, has been quite a bit faster on the AMD GPUs. At least for this generation, and that seemed to also be the case with the MI300A series, qualitatively at least. So if we look historically, there have been 2 Gordon Bell Special Prizes on implicit finite element analysis. One in 2002, and this was a group at Sandia using FEDDP as their, so that's a multi-level domain decomposition technique. And then in 2004, Mark Adams was at Sandia Livermore at that time, and this was using smooth aggregation algebraic multigrid. If we look at the performance that was coming out of those and we compare to one node of Crusher or Frontier, we actually find that the performance is very much in line. This could not have been achieved using the same algorithms from before. So we can now use quadratic or cubic elements. We solve problems of about the same size. And if you look at, say, this bottom row here, in degrees of freedom per second per load step, we see that there's actually a huge benefit. We have realized more than the increase in peak bandwidth in performance benefit, and the older methods are much slower, or the assembled methods are much slower if you were to turn to quadratic or cubic elements. So it's kind of an interesting point of context. So I want to turn attention to some applications that we have built on this. First, we'll look at phase field damage mechanics. So this is work by Fabio Di Giacchino. He was a member of our PSAP project. He's an expert in metallurgy, phase field mechanics. He is currently on the job market. But the approach here is to have a viscoelastoplastic formulation written in Hanke strain, which is a logarithmic strain formulation, allows you to do large deformation. At the level of linear systems within a Newton method, this gives you a block system where the A matrix represents the the finite strain momentum balance. So that's some sort of elasticity or inelastic operator. And then the D piece has the structure of a screened Laplacian. This does depend on the specific damage model, but the general structure, the algebraic structure, looks like this. So within this formulation, there is a viscoelastoplastic representation, and then we've been experimenting with something we call damage viscosity, which allows you to have it allows you to control the speed at which the brittle fracture propagates. So this is your very standard kind of 2D test problem. There's two conditions. One is that you have a clamped or fixed boundary at the bottom, and then apply a displacement at the top, and we'll see that crack open. You can see that on the left lower part where it kind of propagates and it reaches that bottom corner. And then this other configuration, the clamp is applied on the left. It is supported but allowed to slip on the bottom, and then a displacement is applied above the crack, and that causes the crack to open, and you can measure how far away from the wall it is. Anyway, this is a kind of test problem. We've then extended this to the mechanics of bonded, like viscoelastic binder with a bonded granular material. So a test problem here, we create a cylinder that has a bunch of these ellipsoidal inclusions, these kind of grains. Those are randomly distributed, and then we'll have multiple realizations with that kind of distribution. And then lubricated or non-lubricated platens for the top and the bottom. So that's like a frictional contact model. And so you can see the effects of the viscoelasticity and then this damage viscosity in the load curves. So these are force displacement curves in the upper right, unlubricated and then lubricated. And then you can see the fracture patterns that emerge. And these like X-type fracture modes are observed experimentally for this kind of situation. The solvers converge fairly well. This stuff was run on, I think this was run on Tioga, and then I'll show you other things that were run on Tuolumne. So we use a P multigrid setup. You do have to represent the rigid body modes for the smooth aggregation algebraic multigrid, but we don't actually include the damage field because it ends up not being necessary. It is a screened Laplacian, and the characteristic length scale over a time step is not enough to require going through the whole multigrid cycle. So there's kind of there's the P multigrid part of going from quadratic to linear elements. And in this case, the grains were meshed in using Gmesh. I'll show you things with material point methods later. So the grains are meshed in. We drop from quadratic to linear elements. There is smoothing that occurs there, but the algebraic multigrid beyond that does not represent the damage field. If if that characteristic length scale was somehow much longer, then you might want to include it, and but it makes the algebraic multigrid a little bit heavier to include it. Yeah. There is in metallurgy, there is this concept of particle reinforced materials. So what we do here is we're going to take 3 random realizations of particles. These are much more sparsely populated than on the previous slide. We're going to put these particles in. We're going to have this sample in tension, and you get a force displacement curve like we see over on the right. These, with the different distribution of the particles, are still leading to very similar force displacement curves. And then you can look at the fracture that ultimately occurs, and we see this cup-cone fracture modality, which is also something that you observe experimentally. Stefano Focusato is a PhD student that recently joined our group and has been looking at fluid structure interaction, developed an interface to Precise, which is a FSI coupling package. And so this is Radel doing the structures simulation for this example, which is part of this example is like a standard test case within Precise. We are in the process of adding an interface for Honey, which is our compressible turbulent flow solver, which I'll look into in a minute. And I need to make this a slide. One other piece, a number of you have met Rezgar Shakeri. He has developed plasticity models that are written entirely in terms of free energy and dissipation potential. So this greatly reduces the amount of work that you have to do in deriving a return mapping algorithm. Instead, you can provide functions that evaluate just the free energy and dissipation potential, and then the whole return mapping algorithm is derived using enzyme. And this work has been mainly in Henke strain, though we have also done these plasticity models in a multiplicative formulation. The Henke strain greatly reduces the cost of the return mapping algorithm compared to a full multiplicative formulation. And it's appropriate in a lot of settings, but it's actually, it's interesting where the Henke strain formulation deviates from the full multiplicative formulation. So everything that I've shown is based on libCEED. libCEED is this algebraic framework. FEM has support for using libCEED for operator evaluation, and it gets us transparent access to both CPU and GPU implementations through all of the vendors. We have support for different languages. We have these new at-points kernels, which I'm going to take a peek at here. Oops. So I think you all have probably seen the standard seed representation. What we're going to do is we're going to move from these quadrature points being regularly distributed, and we're going to have the concept of quadrature point can now be arbitrarily distributed within elements. And so internally, we will evaluate the finite element basis functions or transpose type operations. We have efficient GPU implementations for all of these operations to and from particles. And it works within the kind of consistent libCEED interface. So all the algebraic components look the same. But now you're evaluating on particles, which can carry information, and those can move through your mesh. We do require that the user locate the points in terms of which element they are associated with. But that's something that any mesh management package that deals with particles, it's a very standard operation. What I'll show uses DM Swarm, which is the component in PETSI that handles this. And we have contributed a number of things to DM Swarm in the conduct of this work. Yeah. We are going to look at a press of, this is a mock HE, but it's an IDOX S-stain mix. So you have a bunch of grains. These are kind of coated in the viscoelastic binder. They're called prills. We, as part of the PSAP Center, we had a bunch of CT imagery of these samples prior to pressing. And then there were experimental presses of those, and we wanted to simulate the pressing process. So you can see like there's lots of weird voids before the press has been conducted. We took the voxel data from the CT scans and sampled that onto material points, and that becomes an initial condition. We are working with hex meshes that in general conform to the cylindrical boundary, and then we have platen boundary conditions on the top. We'll see what this press ends up looking like. So we get a very large deformation. This is not something you could simulate with a standard finite element method because the grains kind of grind against each other. There's too much motion within that process. Zach has also used this this at points evaluation to develop bilateral contact algorithms. And it turns out it's a really handy primitive for that. So even if you're working within standard finite element methods, within contact mechanics, you end up having to sample or evaluate basis functions from one element onto points that were somehow associated with a different element. And so they're not going to line up. It's not a standard quadrature. And he's developed the ability to segment the interfaces between two surfaces that are potentially in contact to develop a consistent integration scheme. Those are very non-standard quadrature locations, but then we can evaluate contact on those surfaces, and this leads to methods that can pass patch tests and form a reliable basis for contact. I want to look over at scale resolving compressible turbulence, because this is another application that has largely the same structure. So in this work, we're not using the at points evaluation. We have developed data-driven closure models, and that's something that has run online. We, as of recently, have RAND support within this. But anyway, Honey started as the fluids example inside the libCEED repository. And then it was known sort of colloquially for a while as seed pasta. Pasta is the package that Ken Jansen has developed since the 90s for stabilized finite element simulation of turbulence. And then it is now called Honey, and it lives in its own repository, and it has various people contributing to it. So the general algorithmic framework is stabilized finite elements. We have support for pressure primitive variables, entropy variables, and conservative variables. And that's actually kind of an interesting and non-obvious choice, but we are generally using the pressure primitive variables. There are times when the entropy variables would be preferable. For low Mach simulation, conservative variables are not a good choice. We have been doing experiments both with this the generalized alpha methods, which is what Pasta has used historically since the 90s. And that's a good approach. It allows you to have um, a bit less dissipation than a BDF2 method, but enough. So it's a second order method that gets you between trapezoid rule and BDF2. Trapezoid rule doesn't have enough damping, and so you get kind of ringing effects, whereas BDF2 is kind of too dissipative. We have done a bit of work with Rosenbrock W methods, and those are actually quite promising from an efficiency standpoint. When we are running in nonlinearly implicit mode that is using generalized alpha, typically that leads to 3 Newton iterations per time step, with quite coarse tolerances on the linear solve. And in that mode, the first 2 linear solves are very cheap, say 5 to 15 Krylov iterations, but the third one is stiffer. If we run with Rosenbach W, it's a linearly implicit method, but you need a tighter tolerance on the linear solve. And so if the cost to assemble was large, this is a benefit because you only need to assemble once. On the other hand, if the cost to assemble is negligible, it ends up being a similar number of iterations, of like total Krylov iterations. So we have done a variety of benchmarks. The thing on the right is just for this flat plate benchmark. This is a like displacement Reynolds number of about 1,000, and it develops to 14 or 1,500 across the plate. But you see here that the higher order methods are much more efficient, like an order of magnitude more efficient in many cases than if you were using sparse data structures, and more than an order of magnitude more efficient than the strong scaling limit using pasta historically. So that's enabled us to do some kind of interesting new work. The Boeing speed bump is one representative test case that we've been doing DNS for. It's really interesting because it's a very simple looking problem, but it does have strong pressure gradients, and RANS models catastrophically mispredict the skin friction coefficient. And like an interesting bit of science here is it is not in the wake, in the adverse pressure gradient part, that the worst errors are committed. It is actually in the favorable pressure gradient part. And so this tells us a certain kind of non-local effect that RANS currently doesn't have a good way to capture. So there's this question that keeps coming up at NASA's high lift prediction workshop of, is it possible for RANS to predict high lift configurations for the right reason? And that last bit I think is really important and what makes it interesting. There are 2 groups that have run simulations of that speed bump at Reynolds number of 2 million. And we find even for this configuration, which seems like, say, overset grids and structured grids, they feel like they ought to be a good solution. And yet when you run the numbers, it doesn't seem that way. It seems like unstructured elements and implicit solvers are awfully competitive to just plain better. And so I think there are some lessons we can take from that in terms of choices of methods. One thing we've been working on um, and have integrated within Honey, have been doing a lot of work with, are these data-driven closure models. This work was the thesis work of Aviral Prakash, who is currently a postdoc at Sandia. So we can do online training, which is running the DNS. The problem is DNS produces an overwhelming amount of data. We can train the closure models from the DNS while it's running live. And then the closure models have been designed to be reference frame and unit invariant. So that sort of harkens back to rational mechanics, and it's a fun like representation activity to make a expressive and flexible model that still respects all of the invariants that they ought to. We have RAND support. We have like unstructured measures of distance that comes from solving a P Laplacian. So it's a PDE-based, kind of unstructured distance measure, which gives us all the ingredients for DDES, which should come online within the next month or two. Sorry, we have looked at that. So reflecting on all of this, we have, how are the performance models changing? And so if I look at iterative solvers, these, since the 90s, have been overwhelmingly limited by bandwidth, especially when we're using assembled sparse matrices. That has really low arithmetic intensity. The hardware since the 90s has been much larger. Preconditioners, if we're talking about scalable preconditioners, these are also heavily bandwidth dependent. If you're using direct solvers, and like a lot of structural mechanics is quasi 2D to an extent, even if you're not using shell elements, it can be quasi 2D. You can often go a long ways with direct solvers. But there is a bunch of leaf work, and then there's dealing with the supernodes. And so compute still matters there. If we look at these matrix-free methods, it is still mostly bandwidth limited. We use more flops relative to the bandwidth. A lot of that is just because we found lower memory representations for what we need. So working out how to further reduce that storage, like when is it beneficial to recompute something, having a flexible way to choose what do we store versus what do we recompute is quite valuable. I think there's a lot of opportunity in working with automatic differentiation tools to decide what should be stored versus what should be recomputed. It's very important to have kernel fusion. So within libCEED, there are what we call the gen backends. And probably some people in this call have participated in the development of that. But that fuses everything into a single kernel that does restriction to elements, possibly from many different from many different vectors of many different inputs that are going to be needed. Evaluates basis action using tensor contractions to get to quadrature points. Does the user-defined operation that needs to happen at quadrature points, and then comes back out with the transpose operations. That's a lot of stuff to put into one kernel, but if you don't do that, you have to store intermediate representations, and that hits you really hard on the bandwidth. So there has been a tendency with GPUs recently to prioritize the reduced precision like matrix operations. those are not very useful to us. Like we need hardware that supports vector style operations, not just matrix. Um, and unfortunately, the most recent generation of GPUs are kind of not delivering that because it's not what large language models primarily need, transformer architectures. Um, so as a principle for matrix-free methods, and something I didn't include here, but that we've done a lot of work on, are finite strain, incompressible, elastic, and inelastic models. And so having a well-conditioned formulation, possibly by including Lagrange multipliers. Lagrange multipliers aren't bad. Yes, they give you a saddle point system, but we know how to solve saddle point systems well. It's a little more sophisticated in the configuration of the preconditioner, but we can do a good job with saddle point systems. That is much better than eliminating and getting, say, displacement only formulations. So we really want to keep an eye on the conditioning and figure out what we can smooth. Often leaving some extra degrees of freedom in avoids like divergence within a kernel. It can simplify the cross-lane operations that might be happening. It might reduce how much auxiliary storage you need. Yeah, there are degrees of freedom, and the Krylov method sees them, but that in and of itself is not need not be catastrophic to performance. So overall, some kind of high-level lessons. You can move from linear to quadratic elements for about 2x the cost, despite having 8 times more degrees of freedom. If you were to say, I hold the number of degrees of freedom constant and I have the choice of going to quadratic elements, it's about a 4x improvement in performance. This should affect the way that we think about mesh generation and modeling of systems. Quadratic elements also give us things like stability for incompressible problems. So there are a lot of choices that are often kind of implicitly made. And this is very flexible for nonlinear mechanics. The ability to deal with these poro viscoelastoplastic models with damage, or to deal with really interesting flow physics. So I'll go ahead and end here. I think there were a couple questions in the chat, and so I'll look at those. And happy to take other questions as well.
Well, thank you very much, Jed, for the really impressive and interesting talk. You're getting some virtual applause here. All right, folks, please unmute. I'll put questions in the chat. Maxwell, do you want to read your question, or should we read it?
Yes, you can read it.
Okay, all right. So Maxwell's first question is, what trans models struggled with capturing separation? I'm not sure on which slide exactly. In one of the slides.
This, I believe, is SA neg, but K epsilon and SST models have similar issues. This is something that's pretty well documented in the literature on these on the speed bump. There have been a bunch of studies about the speed bump, but one of the interesting effects is it's not just a failure to capture separation. It is a misprediction of the skin friction coefficient well upstream of the bump. So the 0 here is where the peak of the bump is. And so everything to the left of that is upstream of the bump. No separation has occurred there, but mispredicting the skin friction coefficient at that point, it causes you to misestimate how energetic the boundary layer is. And yeah, that does affect the separation downstream. but the cause of it, in a sense, at least following the direction of the flow, is in this favorable pressure gradient regime. And so like there have been some assumptions that like, oh, it's about the adverse pressure gradient, part of the simulation, and that's the place where, say, you need some scale resolving method to kick in. But it is not actually sufficient. You need to somehow be looking upstream in order to to correctly predict the flow.
All right, thank you.
I see you also had a question about higher Mach numbers. We have been working with some transonic flows. Those have been more kind of small scale experiments to get happy with the models. So there's an aerospace student who has been working on adding a chemistry module to be able to do hypersonics. Ultimately, we do have a YZ beta shock capturing method implemented, but that has mostly been tested in like shock tube type experiments. So I don't have like large scale simulation results, but we are certainly interested in that regime. And if you have problems of interest, we'd be happy to collaborate on that. I also see a question here from Lucas about the Henke strains. What I have shown is using a Henke formulation. I could I can find an image, or we can share. Maybe it'd be best to follow up offline. I have experiments that Resgar has been doing in like dog bone and other kinds of tension experiments with the Henke model as compared to the multiplicative. And what's interesting is we get very similar force displacement curves, but the stress distribution, like if you cut across the necking zone and you look at the distribution, it is quite different between the Henke formulation and multiplicative.
Okay. Lucas, do you have any follow-up questions or comments?
Dog bone, I agree. This is Lucas. It works great. And then you can even show that gives the same load displacement path. But this is coaxial loading. When you do eigen strains, because you have to calculate a logarithm in the eigen values, and then you have not coaxial loading. So you have in the situation that the plastic strains have different eigenvalues. The total strains, you observe strange softening, even for positive hardening. And that brings a lot of issues with the robustness, because you have artificial localization, you can have, and the other things. And then this was a great disappointment for us when we start to use that in the industrial problems, because we cannot calculate real stuff.
Yeah, different eigenvectors, but we have also been experiencing this, and the literature is clear that it's the same if you have coaxial loading, but even in necking experiments, you don't have coaxial loading. It's for large strains, and so the stress distribution can be different even when the force displacement curves are considered good. It would be really interesting, I think, for the community to have an exploration of that, because it's clearly not like well appreciated in the community what the limit of the Henke formulations are. And I think many people assume that they are more broadly applicable than they are.
I
and
agree.
this causes like a tension. Well, an assumption that the additive structure in the return mapping is representative. And I think we should have more attention on how to efficiently do return mappings for the multiplicative formulation.
At the moment, I will not recommend the Henke plasticity to people.
Thank you. Thanks for calling, August.
Yeah. Yeah, very interesting to hear. Thanks.
Dennis, do you want to unmute and ask your question?
Sure. First, thanks for the really great talk and also great research here. I mean, I've been following this for quite a bit of time now. My question would be on the solver side. I mean, in the beginning, did you recommend to use the polynomial multigrid alone or in combination with an iterative solver?
So I recommend using appropriate Krylov methods, and then the P multigrid coarsens down to linear elements, and then we continue with algebraic multigrid. The course level is very important. I have been interested in using like BDDC or FEDDP as a course level. Unfortunately, the spectral properties of it don't like they don't naturally work in this position. So you can end up with like negative eigenvalues of the composed V cycle if you have an approximate like one application of a BDDC preconditioner on that course level. And so we have been sticking with AMG for some problems. An elasticity configuration of Boomer AMG is we find to be very good. For other problems, especially like very thin cantilever beams, something where the rotational modes become quite important. We have had much better results with smooth aggregation. And so, yeah, and that's like consistent with the theory.
Yeah, let's see.
But yeah, for the structural mechanics stuff, it is always backed by an AMG and inside of a Krylov method.
And have you been able to scale this up on multiple GPUs?
Yeah, we have run on about 1,000 GPUs of Ptolemy for problems with billions of degrees of freedom around, and for the material point stuff, around 10 billion particles. Those are, sorry, I'll skip ahead. Here, get the appropriate visuals. So one thing that we've been doing here is we have a background stiffness. So that there's a technique that the geodynamics community uses a lot called sticky air. Basically to deal with these voids that are within an implicit NPM method, you have to put something there. And one of the techniques was to drop in kind of ghost particles that represent something that is soft and compressible. But it turns out a better way to do it is just to add a background field operator, one that is classically integrated, not integrated through the material points. And that avoids the aliasing concerns in that kind of regularization. And so that has allowed us to do these sort of simulations. What you're seeing here is not the largest number of points, but it's what was convenient to visualize. But we have run these, on the 1,000 GPUs with 10 billion material points.
Interesting. Okay. And how exactly do you deal with the internal variables here across the levels of your polynomial multigrid? Because I mean, if you like change the order, then you can technically reduce the number of quadrature points used, right?
Yeah, however, the quadrature points include the linearization. Like they have nonlinear information, and if you resample onto a smaller number of quadrature points and then reevaluate the nonlinearities, that is kind of like a form of aliasing. It can cause the coarse operator to be a less faithful representation than it would otherwise be. And so we actually integrate on the fine level quadrature points, even when assembling the coarse level operator for algebraic multigrid.
Interesting. Thanks. Didn't do about this one.
Cool.
I want to follow up real quick on some of Dennis's question. You mentioned use Boomer MG for elasticity on the courses grid. Is it kind of the default system-based approach, or is this special elasticity version that Boomer MG has that incorporates the rigid body modes in the prolongation? Do you know?
The full elasticity suite, like from you have a paper around 2010 with Allison Baker.
Yeah,
So
yeah. Exactly.
We had tried that. That configuration itself doesn't run on the GPU.
Yeah, true.
But we worked with Victor on like selecting the configuration, and the one that we've been using runs on GPU and is kind of a middle ground. So I in no way discount classical AMG as a viable approach for this, but the configuration that we had, through that collaboration with Victor, is the one that I'm referring to. When we use it for this system, it is. It's not the one that appeared in your paper, and I think, like with some further work on that, like improving the support for representing the rigid body modes in something that can do setup on the GPU. I think it would be well worth subsequent comparisons.
Yep, agreed. Let's see, Jerome, do you want to mute and ask your question?
Yeah, I was. Thank you for the talk. It's nice work. I guess I had a couple questions. The first one is the work that you did with Precise. That's, I guess it sounds like in your experience too, and maybe that helps explain, but it's been hard for us to get good convergence on using the AMG on these kind of long, thin beam problems. And it sounds like you must have been using like Petsy's smooth aggregation for this.
Yeah, that's what we've been using as course levels. So it's still P multigrid because usually we have quadratic or cubic elements. And then, on the course levels with those thin structures, we have had better luck with smooth aggregation. That should be qualified by, Sanio's 2010 paper on this for hyper, I think it's a viable approach. Um,
Yeah, I guess my main point was it seems like for the solid mechanics, um, my other observation is that a lot of the other things that you've shown, they might have some like contact or smooth discontinuities from the using the phase field stuff, but a lot of the, you might say the loading or the boundaries is kind of like high frequency. Um, in other words, there's a lot of kind of things that are going on, but they're going on at kind of a high frequency, and you don't have a lot of long mode kind of activity going on. And I would imagine that that's actually really pretty nice for the AMG methods and the Krylov solvers to knock down. And um, I guess when we try to run these like larger kind of industrial problems, you end up with some parts that are kind of long modes, long thin things, and then other things that are like more uh, like monolithic altogether. It seems kind of hard to get a nice like solver that works for all of that. That's and but I also say that some of the stuff that you've shown looks really good. So I just wondered what you know there, or what your experience is.
yeah. Representing the rigid body modes is kind of the key to robustly dealing with thin structures or situations where you have like a really weak connection. You get that when you have like a small contact patch or something.
Right.
And so that's very natural within the smooth aggregation structure. It is, you know, less natural. Like it takes more work to incorporate that into classical.
Okay.
And so that's kind of what I'm getting at when I say we tend to prefer smooth aggregation for that kind of problem.
Right.
Um,
Okay.
and if you have test problems, we'd be interested in running those and comparing. Both the P multigrid kind of efficiency side of things and just the robustness.
Yeah, we've been working on it. It's like it's weird because until we get to things of the right level of complexity, I would say that AMG actually works really pretty good. And then we get to a certain level of complexity, and it seems to be kind of a project that we have to do to make a nice unclassified version.
Yep.
And
Yeah.
so that's something that we're working on. I guess my other question was, you mentioned that you have some nice methods to deal with putting the Lagrange multipliers directly in the system, and maybe you wanted to talk a little bit about that because yeah, I would just be interested to let's learn about that.
Yeah, certainly. So for the finite strain incompressible formulations, there's a kind of perturbed Lagrangian approach, which gives you symmetry.
Yeah,
And
I
there is,
no, I understand
yeah,
about the like an incompressible, because then that looks a lot like a fluids code, right? I'm more thinking about things
yeah.
with contact constraints, I guess.
With contact. Yeah, so this is stuff that Zach Atkins has been working on lately. Um, and so he's been exploring a range of formulations. There are these like Nietzsche formulations which don't introduce Lagrange multipliers, and
Yeah,
uh, it's related to penalty methods, but they don't need really huge penalty parameters. That said, there are some kind of serious issues with that formulation. So I'm actually not a fan of it, but it hasn't been compared directly to the Lagrange multiplier formulations very much. We were initially working with unilateral contact, say you're having a moderately soft sample in contact with a rigid platen.
Right.
Zach has been working recently, like, since the PSAP project ended, with bilateral contact. And I think it would be great if he were to give a talk in this seminar, maybe over the summer or something. Anyway, he has preliminary results right now. And I think, he will have more experience with that.
Yeah.
So
That would be great. Sounds good. I guess my one other question, it does seem like, like moving to quadratic can get you some benefits. I guess it feels like from what I've read that in the practical problems, moving beyond that in solid mechanics maybe isn't always, worth it, I guess you would say. And I wondered what you thought about that.
Yeah, so I think that question comes down to how much do you need to resolve geometry? So, and what is acceptable accuracy for you? So, like on this plot, this is like a strain energy as the error.
Right.
But on this plot, if you were way over, like your tolerance is 10 to the minus 2 on this scale, quadratic is going to be the way to go because you just can't mesh the geometry with cubics at a coarse enough level. And so the cubics, which are the square in this case, they give you too much accuracy. You don't need it. Yeah, it's not much more expensive than quadratics when you use the right data structures. But if you just can't generate a mesh for your geometry that's, has such large elements, or it's a bunch of human time to do that, then by all means go with quadratic.
And it's also going to come down to the fact that your singularities in your problems are going to really start to wash your benefits out, I think, in a lot of places. This curve doesn't have the singularities in it, right?
This does have the singularities. So
Really?
this problem has it has these singularities, these very weak singularities all the way around here, and then it's clamped on the back boundary condition, and so you do have singularities at the corners there. I removed my
those singularities go away as you refine the mesh except at those back corners, right?
So with every order element, if you do H refinement, you get the same slope on this diagram. So you can look at, say, H refinement of the blue or gold boxes, for example. And those are cubic elements with high order geometry. You're getting the same slope as with linear and quadratic elements. That is a product of the singularities. If you didn't have singularities, you would get different slopes. But the higher order methods deliver so much better constants. And so I think it comes down to what mesh is convenient for you to make. And if you can just, you make a quadratic mesh and it gives you enough accuracy and it's whatever is, kind of as coarse as is convenient, then you're set.
To some extent, this is the argument for NURBS, right?
It is to an extent.
In that you're getting the same order of accuracy on the mesh as you are on the geometry. whatever, however you've defined the geometry, right?
Yeah, so I'm actually not a fan of NURBS finite elements, um, partly because all the complexity is in like the T splines or U splines. It's
Yeah,
how you connect the NURBS patches,
right.
and the quadrature is so much more efficient with C0 elements than with elements that have higher continuity. And
Right.
so the cost of your method, like how many quadrature points per degree of freedom, is just way higher when you have these the high degree of continuity. You also have big vertex separators. So if you ever want to use a sparse direct solver, the cost of NURBS is way higher.
Because the bandwidth goes up and stuff.
Yeah, and so we can debate about dispersion properties of those methods, but uh, yeah,
Okay.
uh, I'm quite skeptical of like NURBS as an efficient general purpose, kind of uh, approach for solid mechanics. Um, I'm personally, I'm quite happy with C0 elements most of the time,
Hmm.
and C0 elements are very efficient, but the big question is how much accuracy do you need? Um, if you generate your mesh of the geometry and you find that's not enough accuracy for me, then P refining is likely to be much better for you than H refining.
Okay. Well, yeah, thanks. I know that maybe that got off topic a little bit. I just, it's a pretty interesting topic for us. So thank you so much.
No, no, no. This is exactly on the
Yeah,
topic. That's why we have 30 minutes after the talk. Thanks, Jerome.
yeah, absolutely. And feel free to drop me an email. I'm happy to chat further or to do comparisons. So
Great.
Yeah,
Thank you so much.
just to mention something, Jerome, this issue with AMG for long thin structures, I think we've seen it also in other settings in electromagnetics. If you have a long coil, for example,
Yeah.
also an issue, and I think it has to do with additional eigenvectors that are essentially a 1D eigenvectors that are not and are global and are not handled unless you somehow incorporate them in the prolongation, and that's the rigid body modes there. But I wonder if one could tackle this a little bit more directly, and special solvers can be developed for that. So I think it's pretty interesting.
I think it would be great. Yeah.
I've been thinking about this now a bit, and why exactly should, if we change the quadrature order between the levels in a P multigrid, why should the intermediate levels be a less faithful representation of the hierarchy? If I understand this one correctly.
so it's about resampling and reevaluating the nonlinearity. And so, for example, the higher order basis can produce a sharper gradient. So if you suppose like a shear thinning rheology in a boundary layer, or you're thinking about like a plasticity model, where there's some localization that's happening. If you're using your higher order basis function, you generate that steeper slope, that like larger stress or larger strain. And so that gets sampled onto the quadrature points on the fine level, with the quadratic or cubic basis functions, let's say. So the problem you want to solve has this plastic yielding, or it has this substantial shear thinning. Then you go to a linear element, so you p course into the linear element. If you then evaluate the strain or the strain rate or whatever from that linear element, it's smoothing it out over the whole element. It doesn't generate those steeper gradients that are associated with the higher order basis functions. And so you may find we're not plastic yielding in this scenario because it's smoothed out. And so that's why it becomes a less faithful representation. If instead you evaluate at the higher order quadrature points, then you see the nonlinearity. If it makes it soft, for example, that is resolved. There is, you know, a question about aliasing and like, you know, how much does that matter to you? The other kind of practical issue is, for example, in a plasticity model, usually your state variables live at quadrature points. And so, you know, as the plastic strain accumulates, it's defined at the fine quadrature points. If you wanted to use a coarse quadrature, like if you wanted to use a 2-point Gauss quadrature for your linear elements instead of, you know, the 3 or 4 points per dimension that you would get for a typical quadrature for quadratic or cubic elements, you would have to somehow transfer that nonlinearity over to the coarse set of quadrature points. And that's not a well-defined operation, especially when you're dealing with heterogeneous materials. But it, you know, just in the case of a plasticity model, it's already a problem. So we prefer to just reevaluate at the quadrature points where the materials are known, and you know where there's one evaluation of the nonlinearity, and then the P multigrid is dealing with that linearized model in a consistent way.
Makes sense. Thank you.